Hi guys. So we studied proportional controllers and proportional plus integral controllers. Let's now have a look at proportional plus derivative controllers, what they are exactly and how they work. What is PD or proportional plus derivative control exactly? As usual, we will give it our first look through a block diagram. So we start with our reference signal, RT, to which we subtract Y'(T), our output. This gives us the error of the system. Now, like for the PI controller, our controller in this case has two branches. One of the branches is the proportional branch with the gain Kp. As usual, it just multiplies the error by the gain Kp. And we now have an other branch where the error is multiplied by a derivative gain Kd and then differentiated. So we talked about this in the previous lecture, and in Laplace transforms, a differentiation is just a multiplication by s. And this actually allows the controller to look in the future. It looks at the rate of change of the error to predict where it is going to be at the next point and try to minimize future errors. So we then compute a signal from these two. So we have Kp times Et and we have Kd times Et, all of this differentiated, and we make the sum of that to output the control signal. Ut is equal to Kpet plus Kd multiplied by the differential of the error. You will notice that Kd is out of the differential simply because it is a constant. So differentiation doesn't apply to it. You can put it out of the differentiation. So we feed this control signal into our plant GPS, and then again this outputs our output signal Y'(T). To sum up, we essentially added a derivative term which can be used to improve transient performance and stability of our system. It acts on the derivative of the error, thus produces a fast answer, but cannot act on a constant error as the derivative of a constant is equal to 0. So the error actually needs to be changing and varying for PD control to have any effect on it. Let's look at the structure of this kind of system. So as usual, the open loop transfer function is GS, and it is the controller transfer function multiplied by the plant's transfer function. So here it is GS equals Kp plus Kd multiplied by S because of the differentiation multiplied by the plant transfer function. So the output Y'(S) is equal to the open loop transfer function multiplied by the error ES. We also know that the error ES is equal to the reference input RS minus the output Y'(S). So eventually, we can write that the output Y'(S) is equal to GS multiplied by RS minus Y'(S). We can develop all this to give that the transfer function of this system from reference input to output is equal to Y'(S) over RS equals GS over 1 plus GS itself equal, once feeding in all the appropriate terms, Kp plus KdS multiplied by GPS divided by 1 plus Kp plus KdS multiplied by GPS. So if you look at this, you can see that first of all, there is a S in the numerator. So this created a new 0 in the numerator, and as we've seen, this will most likely lead to an overshoot in the response of the system. It can actually be avoided by placing the derivative term in the feedback of the system, so the signal going from the output back to the reference to build the error, and we'll look at this in the next lecture. As usual, let's look at an example to see how exactly we can apply PD control to control specific systems. So here we are going to look at the model of a DC motor used for position control. Its planned transfer function is GPS equals 699 divided by S multiplied by S plus 1.95. So here we want a critically damped control with a settling time of 0.4 seconds. So we just developed in one of the previous slides the transfer function from the input RS to the output Y'(S) for our system. And it is equal to Kp plus Kds times GPS divided by 1 plus Kp plus Kds multiplied by GPS. As usual, the characteristic equation is the denominator of this transfer function equated to 0. So this gives us 1 plus Kp plus Kds, and we replace the values for the planned transfer function GPS to give 699 divided by S multiplied by S plus 1.95. We can eventually develop this, and we finally obtain S squared plus 699 Kd plus 1.95 multiplied by S plus 699 Kp divided by S multiplied by S plus 1.95. For any critically damped system of second order, we can write the characteristic equation as follows. S squared plus 2S multiplied by the damping coefficient multiplied by omega n plus omega n squared equals 0 with the damping coefficient equal to 1. We also have, as usual, Ts is equal to 4 divided by omega n. As we want Ts to be equal to 0.4 seconds, we can calculate that omega n has to be equal to 10 radians per second. So plugging in all these values into our equation, we can write that the characteristic equation for the performance that we want of 0.4 second of settling time and a critically damped system is S squared plus 20S plus 100 equals to 0. Similarly, from the previous slide that we have, we developed the full characteristic equation of our actual system. As it has to be equal to 0, its numerator has to be equal to 0, so we can write that the two equations are actually equal. On the left side we have the characteristic equation for our system, and on the right side we have the characteristic equation for the performance we want our system to have. You can then identify each term by each term, so 699 Kp is equal to 100. The part multiplied by S is 699 Kd plus 1.95, and that's equal to the same part on the right side, so 20, and that gives us a proportional gain of 0.143 and a derivative gain of 0.026. So the system's transfer function actually becomes y apostrophe s divided by rs equals 18s plus 100 divided by s squared plus 20s plus 100. So we now have a transfer function for our system that we calculated by finding the gains for the derivative part of the controller and the proportional part of the controller in order to achieve a specific performance, in this case a 0.4 second settling time and a critically damped response. So we can now plot the response of our system. As you can see, it actually does get pretty close to our final value. A steps response, by the way, guys, is a response after an input of 1. As you can see, it gets quite close, if not perfectly matches the input of 1, but we do get a slight overshoot that is due to the 0 that you can see here because we have an s in the numerator of the transfer function. By the way, as a little note, I just want to highlight that all these plots, I actually produced them using MATLAB. I will probably do a course or a lecture about how to use MATLAB and Simulink to create control systems later down the line. So this concludes the lecture on proportional plus derivative control. If you have any questions, please do not hesitate to ask me. And in the next lecture, we will look at a way to actually remove this zero and remove, therefore, this overshoot in the response of our system.